All right, ladies and gentlemen, we are going to do our forces and free body diagrams, which is going to be really our forces notes number 1. If you'll get a paper and something to write with, these will be really good things to make some notes over, as well as to add to your information once you get your package tomorrow. I apologize for not handing those to you in advance. All right, so what is a force? We basically have to break that down first. A force is any influence that can change the velocity of a body. Okay, remember velocity is the speed and direction, so a force can either change the speed or it can change the direction because velocity are both of those. Now forces can act either through the physical contact of two objects, like a push or a pull, or at a distance, which is what we'll call field forces. We primarily in AP1 will deal with contact forces since we're dealing mainly with mechanics. Now field forces come more into play with AP2. So just to let you know, a couple of examples. We'll deal with frictional force in this class. We'll deal with tensional force, which is any type of ropes or strings, things like that. We'll deal with the normal force. We'll deal with an air resistance force, which is really just a frictional force. It's a specific frictional force. We'll deal with an applied force, which is actually something that you put into it. And we'll deal with spring forces. At a distance, forces that we will talk about will be gravitational forces. That's one of them that we talk about here in kinematics. But the electrical force and the magnetic force are primarily discussed in AP2, and we go into great detail there about those. All right? Now, how do we measure forces? Well, we measure them using a spring scale, and it's used to measure the forces. Spring scales you've seen in various places, like the grocery store. When you look at how much your produce is going to weigh, lots of times they have those scales, and that actually is just that the spring inside the scale is going to stretch to an amount that's proportional to the force that's being applied, and that's then calibrated or scaled so you can read that force. All right? When you get on your balance or your scale at home as well, that's really what you're doing also, but you're just pushing down on a spring instead of the spring stretching. So, what is weight? A lot of people want to say that gravity and weight are the same thing. Well, they're not. Weight is actually a gravitational force with which the Earth attracts bodies or objects. Okay? So, weight is a vector value, and it's different from mass. Mass is a scalar value. You remember we talked about the difference between vectors and scalar. Vector has magnitude and direction. Scalar is just a number value. The weight of a body varies with its location near the Earth or other astronomical bodies, so it really deals with gravity. Whereas mass is the same everywhere we go. I have the same mass here on Earth that I'll have on the moon, unless I lose a body part somewhere along the way. But otherwise, my weight, I would much prefer to talk about my weight on the moon than on Earth. And that's because gravity on the moon is less, and so my weight value is actually less as well. So the weight of a body is actually a force that's caused by it being accelerated downward by gravity. So the formula for this is weight equals mass times gravity. So weight is a force. Mass will be in kilograms, and gravity is in meters per second squared. Here on Earth, we used gravity as 9.8 meters per second squared. Weight is going to be measured in newtons for this class, and mass will be measured in kilograms. So really, a newton is a combination, or what we call a derived unit, because of the fact that we put together kilograms, meters per second squared. And we abbreviate it and make it a derived unit, and we now know it as a newton. So 1 newton will be 1 kilogram meter per second squared. So what units are used for forces? Well, in the metric system, like I just said, we use a newton, and a newton is comprised of kilograms and meters per second squared. Whereas in the English system, which is really more what we use here, that's actually a pound. And a pound is created with something called a slug, and I don't really know that I want to talk about my mass in a slug, and acceleration done in feet per second squared. So that's where that's a little bit different. So we will use, in this class, we'll go ahead and use our newtons because that's just easier to deal with because most of you haven't heard of a slug for your mass before. So conversions or equivalents that you need to understand. 1 pound is 4.45 newtons, and this would be something that we could use dimensional analysis wise, so you need to make sure you make note of that. And then 1 kilogram weighs 9.8 newtons, which also is equivalent to 2.2 pounds. So this is really more of a newtons to pounds conversion as well. But if we're talking just about 1 kilogram, then 1 kilogram, that's the conversion that you could use. So how do we describe forces? Well, forces are vectors. Vectors have a magnitude and direction, which means we're going to draw them as an arrow. And they're going to have a tip and a tail, and we can have them in the same plane with each other, and we can add them, and we can have resultants, and we can have them on different planes. And if we have them on different planes, then we'll end up having to look at a resultant that has an angle with it. So we're going to approach forces just like we did vectors. And so we're now going to have them, and we're going to use them in trig, and we're going to talk about them in planes, just like we did with linear motion. So we'll now use those formulas that we used in linear motion that we also applied to projectiles. We'll then be able to apply them to forces once I show you another formula that will be in play. Okay? So when you come to class tomorrow, we will be dealing with a free body diagram, which is where we're going to actually show forces that have a magnitude and direction. Free body diagrams are diagrams that are used to show relative magnitude and direction. So really what they are is we're going to use arrows to show directional information, but the size is going to reflect the magnitude. The direction is going to be the direction that the force is acting. Each force arrow in a diagram will be labeled to indicate the exact type of force that exists, and we'll talk about all the different types of forces tomorrow in class. And then in a free body diagram, the object is typically going to be represented by a box or a dot. I like boxes, and so then I'll always deal with X's going left and right, and Y's going up and down on the box. So we'll talk about that. And you always want the tails of the vectors to be on the object. Then the tips will go the direction that they're supposed to out of the box. So that's kind of just a short, brief concept about forces in general and free body diagrams. Tomorrow when we come to class, we'll work on free body diagrams and go over the different types of forces. See you then. Bye.